right, so here we're looking at the basic hydrostat system. So far, we've got our hydrostat pump and motor. Closed loop is shown. We've also got our charge pump, charge checks, a neutral charge relief, and we're showing the third place that the oil goes from the charge pump. We've got a little orifice right here, and then it says off to the DCV. What does that mean? What's the DCV? It's our displacement control valve or directional control valve. That's the valve that you're actually opening and closing a spool when you move the handle in the cab. All right, when you move the handle in the cab, maybe there's a physical linkage between the hydrostat lever in the cab and the physical lever on the pump that moves the spool. Or the linkage that controls the spool more correctly. There may also be just a sensor in the cab and a controller that moves or that changes the current going to some solenoids that dictates how far that spool moves. All right, we're not going to bother drawing that on this diagram. We're just trying to keep it simple. So everything we have right now does give us a working hydrostat system. This would work. There's a few important things missing, and one of them is, what happens when the pressure gets too high in the system? I mean, a hydrostat system, it operates at pressures easily 6,000 plus PSI. If we start to exceed those pressures, we're going to blow stuff up. So one of the things that we'll do is we'll add in some protection. Now, I'm going to draw this to represent what happens in a typical, very simple 20 series Sunstrand hydrostat. There's three ways the reliefs will work. I'm talking high pressure reliefs here. And one is where it's a simple crossover relief. And that just means that if the pressure gets too high on one side, we just dump over to the other side of the closed loop. Another way is sometimes we'll dump from a high pressure relief into the charge circuit, and then it joins charge oil going back through the charge check to the other side of the circuit. It's effectively still a crossover relief. And the third way, which is how these really simple 20 series Sunstrand hydrostats work, is you've got two high pressure relief valves. Okay, those two relief valves I'm just going to add in our springs here. Those two relief valves, they dump effectively into the motor case drain. And we're going to add all of those lines in just a moment here. Okay, but our motor case drain and our pump case drain are joined together like so. If either one of those high pressure relief opens on the 20 series, the simple old school 20 series, it dumps into the motor case. That's what happens when the pressure gets too high. But there's another thing that we also need, and this has to do with the fact that when you take oil and you start pumping it around in circles at very high pressure and sometimes reasonably high flow, that's not a huge amount of flow, but it gets up there, probably 30, 40 gallons a minute if you're really clipping along. What are we going to do? We have to have a way to cool that oil off, but that oil's busy running in circles, right? So what do we do to cool the system off? We have to add in a loop flushing valve and a purge relief. Okay, and there's different terms that are used for those items. Your loop flushing valve is sometimes called a shuttle valve. Your purge relief is sometimes called a forward and reverse charge relief. But where those fit in the system is over here. Your loop flushing valve is a 3-position, 3-way spool valve. Okay, that 3-position, 3-way spool valve, because it's 3 positions, is going to have 3 envelopes. Okay. It is effectively pilot operated. And it's a three-way valve because it looks like this. Coming off of that valve is your purge relief, okay? And that purge relief is going to join up with, or dump into, more correctly, the motor case flow, okay? We're gonna hook up the rest of this. We're gonna take a line from each one of the drive loops here, your forward and your reverse. And those lines are gonna hook up, and they're also gonna act as the pilot pressure that moves that valve side to side. So my loop flushing spool, let's assume that forward and reverse, those are my directions. Let's assume that we're traveling in the forward direction. So as I travel forward, the spool is going to be pushed down. My loop flushing spool gets pushed down. Now, one thing I don't want to do is I don't want to dump my forward drive pressure through the purge relief and into the motor case, because then there's no reason for the motor to turn. Oil's going to take the path of least resistance. So we're just going to block off that direction. But we're going to join the reverse side, which is now the return side of the hydraulic circuit. We're going to join that to the purge relief. And what that does is it lets some oil vent out of the return side of the closed loop. And however much oil we vent out the return side, we just make it back up through the charge check to continue filling the charge pump. Okay, and that's how we make sure that, not the charge pump, the hydrostat pump, make sure the hydrostat pump stays fully charged with oil. Opposite happens when we take a look at if we're in the reverse travel direction. Okay, shift this valve up. What are we going to do? We're going to want to block reverse so we don't just dump it out through purge. And we're going to take forward, which is now the return side, and dump it through the purge relief. Okay, we're not dumping all of the flow, we're just dumping a portion of the flow. All right, so now we've got a few more components on here. Let's add to our legend. Okay. So we're at 5, so let's go 6. Forward and reverse high pressure reliefs. Okay, 7 is going to be our loop flushing spool. And 8 is the purge relief. Okay. For 9 and 10 there, 9 will be filter, 10 cooler. So aside from what happens with the DCV and the servo pistons, we've got a fully functional hydrostat drive system here. There are some additional features that a lot of the newer systems use, a lot of the more complex systems use, but every system has got these basic components. All right, the next thing that we're going to look at here is where would we be putting gauges in the system? Where would we be putting flow meters in the system? What kind of pressures could we expect in different areas in the system? So first of all, if you got a problem with a hydrostat, chances are you're going to test it out, see if it works or not. And then you're going to grab a couple of gauges out of your box there, throw some gauges on and take a look at what your pressures are. One of the first gauges I would usually grab would go over here. Okay. And this would be charge pressure. I grab another gauge and I put it over there. I'd actually grab two. I'd put one on forward and one on reverse. I'm just going to draw one on this diagram for now. But this is drive pressure. So I got charge pressure, I got drive pressure. Another gauge that I may put on would be case pressure. Now, when I'm measuring case pressure, I might be using that as an indication to figure out if there's a significant rise in case pressure, that could be pointing me towards, let's say, excessively leaking rotating group in the pump or the motor. So if I see a pretty significant rise in case pressure when I load that system down and do a stall test on it, to me that says there's a good chance I've got a lot of leakage. Okay. And the other thing that I'll usually try to do, this isn't going to be the first thing I do, but if I got to do some pretty specific troubleshooting, say for the charge pump or for excessive case flows, is I'll go ahead and I will grab a flow meter. And if I put a flow meter over here, this would be motor case flow. If I put a flow meter over here, this would be charge pump flow. The trainer that we use here at the college has got flow meters permanently mounted in both locations. When we're looking at the charge pump flow, the reason that's putting a flow meter just before the cooler and the return filter, the reason why that measures charge pump flow is because everything that got sucked out of the tank by the charge pump has to return to the tank at some point. It's a fixed displacement pump. We can't just pump oil into a system without it coming back out. Otherwise, it would pressurize and something would burst. All right. So the oil that comes out of the tank goes through the charge pump. It goes to wherever it needs to go, but eventually it collects out of the case drains and it goes through the filter, goes through the cooler, and goes back to the tank. The only other thing that you might do is sometimes you'll put a gauge on if you suspect the reason that you've got problems with your hydrostat has to do with, let's say, collapsed suction line or some sort of restriction in the tank. Maybe you'll measure suction going into the charge pump. Let's talk about pressures. When your charge pump is, well, when the engine's running and the charge pump's turning and the hydrostat pump is turning, but we're not actually driving anywhere, the hydrostat pump is going to be sitting with its swash plate in neutral. There's no flow in the forward and reverse drive loops. So the charge pump is going to start pumping, but the oil coming out of the charge pump really has nowhere to go because there's not going to be any rotating group leakage. My loop flushing spool is in the neutral position, so there's not going to be any flow through the purge relief. So that means that I've got a pump that's flowing oil, and none of those areas need oil. So it's going to end up going to the neutral charge relief. That's why we have it there. Now, neutral charge relief, it's going to open up, and I'm not going to give you any hard numbers here because it really depends on the system, exactly what it's going to be. But for our example, let's say it would be opening at 300 PSI. So in neutral, I got 300 PSI charge pressure. Let's say that my purge relief over here opens at 250 PSI. All right. Right now, that doesn't matter because that relief valve isn't really hooked up to anything. Let's say that my high pressure reliefs open at 6,000 PSI. If I shift into forward or reverse, as long as the pressure in the drive loop doesn't get any higher than 6,000 PSI, it's going to make the motor turn. So when I shift the swash plate, or I use the control lever to shift the swash plate into forward or reverse, my drive pressure is going to climb. And as my drive pressure climbs, to something less than 6,000 PSI, let's just use 5,000 PSI as our example here, the charge pressure is going to change, the drive pressure is going to change because the machine is moving. There's load on it now. So the flow that was coming out of the charge pump, and let's say that flow was 10 gallons. That flow coming out of the charge pump, now it does have somewhere to go. All right, it's got to make up for rotating group leakage. Let's say there's a gallon a minute leakage on the hydrostat pump. Let's say there's a gallon a minute on the hydrostat motor. That's rotating group leakage. And I'm throwing these numbers up here just because they're easy numbers to work with. If you had an actual gallon a minute leakage loss on a hydrostat pump or motor, that would be a pretty big deal. Okay. Usually it's a lot less than that, depending on the system. So anyways, I've got to make up those leakage losses from the rotating groups. So that means my 10 gallons a minute of charge flow, 2 gallons of that is going to make up for rotating group leakage. I've still got 8 extra gallons left. What am I going to do with it? Well, what happens is the flow that's coming out of the charge pump is going to head on down through the charge check, and it's going to join the return oil that was flowing from the motor. Okay, so let's say that my hydrostat pump was pumping 40 gallons a minute. And if my hydrostat pump is pumping 40 gallons a minute, but I'm losing 2 gallons from rotating group leakage, that means that the most oil that could possibly be coming back in here, I need to put out 40 gallons. I'm coming back with 38, 39 gallons. That's a problem. That's why we got the charge pump. Okay, but not only that, the return oil, I'm dumping some of that return oil this way here. Okay, so that return oil, it's coming out through the loop flushing valve and through the purge relief, and we want that. In fact, there's probably about 8 gallons a minute coming out of there. Okay, why is there 8 gallons a minute coming out of there? Well, I had 10 gallons a minute coming from the charge pump. 2 of those gallons per minute are being used to make up for leakage losses. The charge pump is still pumping another extra 8, or yeah, another extra 8. And I'm just going to clean up my diagram here. Okay. So that extra 8, it's going to go through the purge relief instead of the neutral charge relief. And the reason it does that is because at this point, the output from the charge pump has access to 2 relief valves. And if it's got access to 2 relief valves, it's going to go through the one that opens at the lower pressure. All right. So your purge relief is going to be the one that's going to flow whatever extra oil is coming out of that charge pump that we don't need to make up for K-strain losses. So what we effectively do here is we take and dump out 8 gallons over here. And we're just going to stick that other 8 in over on the other end from the charge pump. And that way we're able to vent oil out of the closed loop and put oil back into the closed loop to help cool this thing off. Instead of just pumping oil in circles at high pressure all the time, this gives us a way to cool the system off. All right, so this is what should be happening. And you'll notice that when I shift into forward or reverse, because the shuttle valve or the loop flushing valve moves back and forth, and because that exposes the purge relief to the charge circuit through the charge check, my pressure is going to drop. My pressure drops on a hydrostat system. My pressure has to drop when I shift to forward or reverse. Because if it doesn't, what that means is either my loop flushing spool isn't moving or my purge relief is set too high. And in either case, if I don't have that pressure drop, that's telling me that the only oil that's getting sent into the closed loop is whatever oil was needed to make up for leakage losses in the rotating groups. And that amount of flow isn't enough to cool off the closed loop, and it's going to overheat right away. That's why we've got that purge relief. That's why we've got that loop flushing spool. So get in the machine, slap your charge pressure gauge on, fire it up, look at what your pressure is. Cycle the lever forward and reverse. Does the pressure drop in the charge as soon as that happens, as soon as you go forward or reverse? When you go back to neutral, does it pop back up again? It should. What I just did was I tested 3 different things on this diagram with that one simple test. I tested the neutral charge relief, I tested the purge relief, and I tested the function of the loop flushing spool. The next thing I'll do is I'll lock the brakes and secure the machine, and then I'll do a stall test in forward and in reverse. And when I do a stall test, I'm checking to see if my high pressure reliefs are opening at the right pressures. That stall test might not actually be testing the high pressure reliefs. It may be testing the pressure override, pressure cutoff, pressure limiting valve. It's testing the device that destrokes the pump instead of blowing oil through relief, because it's quite common to do things that way as well. Either way, we're checking the maximum system pressure. Another test that we might do is take a look at case flow. If I take a look at motor case flow, with everything working normally, I should see 0 motor case flow in neutral. And I should see, given the example that I have here, 9 when I'm in forward or reverse, okay? So my case GPM, 0 in neutral, 9 in forward and reverse. All right. If I wanted to isolate just the rotating group leakage in the motor, what I would do is I would take this relief here and I jack its pressure up. And if I jack the pressure of the purge relief up above the pressure of the neutral charge relief, that effectively blocks any purge flow from happening. And when I stall the machine, when I do a stall test, that means that the only oil that's going to be going through the motor case is rotating group leakage. Okay, that's a good way to isolate. There's another way to do it. It's not as simple. That would be to physically block the loop flushing spool from moving back and forth. Sometimes you can do that, but it's usually just easier to jack the pressure up on the purge relief. Okay. If I want to know what the rotating group leakage is on the hydrostat pump, what I'm going to do is I'm going to leave everything working normally on the motor. So that means my loop flushing system's working, my motor case, everything's all normal there. I'm going to take a look at what the flow is during a stall test in forward and reverse. Okay, that's rotating group leakage and purge flow. And then I'm going to take a look over here and I'm going to see what my charge pump flow is, the total charge pump flow. And in this case, 10 GPM, okay? neutral, forward, reverse. But the difference between those two numbers, that is what my rotating group leakage in the pump is. That's how you can figure out how much leakage you have in the pump. Okay. All right, so there we go. We've got all of our numbers down. We've got to look at what happens when we're driving in forward and reverse in terms of the pressures, or drive pressures, charge pressures. We took a look at case flow and understand too that case pressure is going to be higher in forward and reverse if you measure it at the motor, because there's no case flow when you're in neutral, but there is case flow, and wherever you got flow going through restriction, you got pressure. So you will see a jump in case pressure if you're measuring it at the motor when you've got flow going through there, because you're doing a stall test, because the purge flow is happening. All right.